Okay. Right. So today well, for this week, actually, the topic that we're going to cover is volumes of revolution. So, I want to give a bit of a introduction to that. And one thing I want to do is to actually show both methods, try to connect the two together because the main trouble that I think students, what was that? Okay, well, the main thing that students have issue with, or one of the main stumbling points, is actually figuring out which, for a given problem, which method is easiest to apply. So the two methods I'm talking about are the disk/washer method. That's all one. I can spell method. That's one method. I want to put the two like as one thing because they're actually very similar. They're basically the same thing. So I really want to emphasize that they're the same thing, essentially. And then the other is shell method. Okay. So I think that Spencer actually separated these two things into like different lectures, but you really want to actually cover them both at the same time and kind of note how they differ, I guess. Okay, well, the first thing is we probably want to draw a sketch of this typical situation. So, well, first of all, what is a volume revolution? The idea is you have a two-dimensional region that is kind of figured out by just bounding a bunch of different equations, right? That they will describe some two-dimensional region. And then you revolve said region about some kind of axis of revolution. And in easy cases, this axis of revolution is one of the standard axes, the x-axis or the y-axis. If it's not one of the standard axes, then the setup is, you have to think about it a little bit more, but it's also not too bad. Usually it's going to be at least parallel to it. It's just a like y equals 4 or x equals -3 or something like that. You just offset by some amount. But so you end up having this three-dimensional shape gotten about from rotating a two-dimensional thing. Okay. And well, we still kind of have the same thing. It's just that here, maybe I shouldn't have made that so long, but whatever. The primary difference between disk/washer and shell is actually what we consider as our thing to keep track of for creating the three-dimensional shape. Didn't mean to erase that. So you really want to like trace out this red segment and imagine what happens when you rotate that red segment according to these axes. So in the left case, what you get when you trace it out is you get a solid disk, or you could get a washer if, say, the bottom doesn't line up perfectly with the axis. So that's why these two things are really similar. So this gives you a disk. But in shell method, you actually get a cylinder. So visually, what you would see is you'd get something that looks like, I'm trying to draw it. You'd get a cylinder. And so that's how these two things differ. Then the idea is that you want to construct an integral that is going to then, when you calculate it, give you the volume of the region. So this is what you'll typically see when you look up these methods. You'll see these formulas. I'm going to write them now. Okay, well, for disk method, it's just going to be, let's say, just the r of x squared dx, where r, the reason we use r is because we think about this as like the length of the radius. Okay. So for disk or washer method, it's this guy, or it is, in the case of washer method, it's big circle minus small circle. So in that situation, you end up taking a disk and you subtract off a smaller disk, right? Because that's, well, I should also draw the associated picture. So in that situation, the things that you get traced out are, they look like that, except, centered correctly. Okay. So that's all on the left side. On the right side, for shell method, you'll get the formula r of x times h of x. So the way to explain this is the r is the radius of the cylinder. So that would be like in the picture, it'd be this. This is r of x. And then h of x would be the height of the cylinder. So the only issue with what I'm drawing here is that this is kind of sideways. Usually in textbooks, and usually the way that my grade thinks about this at least, is that the cylinder that you have is actually um, upright. So it is more like this, maybe like that. And so, yeah, in this case, like this part is the r of x, and then the height is, well, it actually looks like a height in this case. And so, yeah, there you go. So that's what these two functions are going to be. And well, things will vary a little bit more when your axis of revolution is offset. It's not one of the standard ones, but otherwise, usually you can just read it off of a problem. So, yeah. But okay, so for today, the problems that we were going to deal with are all going to involve the disk or washer method. And Thursday, we'll see problems that involve the shell method. But the question that I want you to keep in mind is, how would you detect which method to use? Because this is kind of made a little bit too simple by us not just randomly giving you like scrambling the order of the problems. Like it's important to be able to tell just by the shape of the problem, the shape of the region, and what you're revolving around, which method is easier. And usually it comes down to drawing this segment. It comes down to like seeing like which way describe like, yeah, which way you would describe the problem more easily. So would drawing the line like this describe the problem more easily, or would drawing it in the other way describe more easily? That's going to depend on the actual functions you're given and on what axis you're revolving. But the thing to notice is that what kind of two-dimensional, or not two-dimensional, but like what kind of shape it creates when you revolve it, that's going to dictate for you which method is actually the method to use. And one way to also see that is if the segment that you're drawing is perpendicular to the axis, that creates a disk. Whereas if the segment that you're trying to draw is parallel to the axis, which is this case, that creates a shell, that creates a cylinder. That's one way to detect these things. Okay. Are there any questions on any of that? Okay. Well, then I'm going to get started on these problems. All right. So, right. So usually we want to draw what the region actually is, because it's always easier to work with a visual sense of like what's going on. So x equals 2, x equals 0, y equals 0, that's just going to be equal axis. We rotate about the x-axis, and we have the equation 2x plus 1. So that's just going to be some kind of a line. All right. And this is the region. This is the region that we rotate about the x-axis to create our three-dimensional figure. Okay. And well, for this, particular shape, it would make more sense to draw the segment like this. It's easy to describe the length of this segment for any given x value. And that's what is necessary. And so like this ends up being disk method in this case. So our integral is going to be with respect to x, and it's going to go from 0 to 2. You can think of this visually as being this red segment is being swept over the region. So it's going to go from the left all the way to the right. That's what the integral is actually doing. And the integral is just summing up a bunch of disks in this case. Okay, and so now we need to square the radius function. So the radius function is just going to be, well, it lines up perfectly to be the actual equation describing this upper function, which is this line. So 2x plus 1, and then you square that. That's the radius. Okay, and so yeah, this would be the integral. And if you just calculate this integral, you'll get the answer. And I suppose I can do that with you guys. Although really, like these kinds of these integrals that you get, you should be able to do them yourself. So obviously we want to expand the inside. I didn't mean to put equals there. And then, well, then you integrate it. So this is going to be 4/3 x cubed plus 2x squared plus x evaluated from 0 to 2. Then when you plug in, well, 0 is going to give you 0. And when you plug 2 in, you're going to get 62/3. So this is the evaluation that you would end up doing. And that's simply 62/3 pi. 62 pi over 3, I guess is the better way to say that. Okay. Right, number 2 is very similar. So we have a line and a parabola. So the line is going to start at 0. The parabola is also starting at 0, and then it kind of just goes up like that. I drew it kind of funny, but sort of purposefully. So the key point here is, well, this is going to be our region, but we need to figure out this intersection point. So what we do is we set the two equations equal to each other and solve. Right. And so when we solve that, we'll get x is equal to 5. So that means this intersection happens at 5, and that tells us the limits of our integral. Okay. Right, I should also say something about, we revolve around the x-axis. Okay. So again, it makes sense to have our segment be like this. Probably there is a way to rewrite it in terms of the other way, but then you have to like really change things. So yeah, this is the easiest thing to do. And well, we have upper function minus lower function. This time, notice that there's a gap between the bottom function and the x-axis. So that's going to make a hole in the disk. So this is actually Washer method. So the formula to keep in mind is the Washer method formula. And well, our upper function is 10x. So that's going to be the big radius. And then we subtract off the small radius, which is the parabola. And we have to square both these radii. And now we just integrate those. Well, first I'm going to simplify the inside. So 100x squared minus 4x to the 4th dx. Okay, now we can evaluate this integral. 100/3 x cubed minus 4/5 x to the 5th. And we evaluate from 0 to 5. Right. Well, it's a bit of a bother to evaluate at 5, but evaluating at 0 is clear to see. So you can imagine that you would probably plug this into a calculator. And if you do that, you'll get 5,000 over 3 pi. Okay, any questions on these two? Okay. Right. Yeah. So number 3, let's see. So for this problem, notice that it has x equals y squared. So that's kind of not the standard thing that you'd expect. So instead, this is a parabola tilted sideways. I don't know if that's immediately obvious, but I would hope it is. I mean, if you didn't know that, you can actually try like plugging values into that equation, and you'd see that like choosing, say, choosing a given x value, you'd find like 2 different y values, and then if you just try plotting it, you'll get this sideways parabola. The y-axis is the thing we want to rotate this time, so that's different. And also we have this x equals 4, so that actually turns out to be somewhere here. Okay, let's say maybe I make that extend a little bit further out. And we want to find the volume that's given by rotating this region. Okay, so the region in question is there. And well, hopefully you can see then that this is the segment that we would track. So if we track rotating this red segment about that axis, we'll get a washer, right? And the big radius is given by the equation 4, and the small radius is given by the parabola, the y squared. And what we need to find is actually the extent of the graph. We need to figure out these intersection points. Okay, so, well, if x is equal to 4, y squared is equal to 4, so y is equal to plus or minus 2. So those are the limits of our integral. And so we still have this pi going from -2 to 2. And it's big radius minus small radius, the big radius being the 4, the small radius being the y squared. And just for redundancy, I'd probably just write it like that, even though we can immediately square that. But if you're ever like checking things, say on an exam, it's usually better to not skip that many steps, so to show more work than normally necessary. Okay, so there we go. And we just integrate this guy. So pi 16y minus y to the 5th over 5, evaluated from -2 to 2. Right. Okay, and so then we plug this in to something. You could probably do this by hand actually, but you'll get, for the first evaluation, 128 over 5. And for the second, you'll get negative 128 over 5. And so this will double up and you get 256 over 5 pi. I've been writing the pi after at the end, so maybe I'll just move it. Okay. All right. Questions? Right. So number 4 is going to be the last problem that I go through. I want to save the last 2 pages to Thursday. Okay, so right, number 4 has an important difference. Right, so instead of the standard axes, we now have this offset axis, and we'll have to deal with that somehow. But the rest of the data, describes the region we're bounding. So this is an exponential. So let's say it starts at 1, it's going to shoot up like that, but then it's going to be asymptotic like that. So that's our e to the x function. Y equals 1 is going to be there. Oh, that was not good. It's going to look like that. And x equals 1 is, let's say that it's over here. So that'll create a line like so. This intersection point would correspond to the value e. Don't really need that, but yeah. And so this is our region, and we want to rotate this about the line y is equal to -2. So that's, I'm going to put that as a dotted line. This is what we revolve around. Okay, so you can see that, well, the segment that you'd want to draw and to track would be there. And that tells you that this is going to be a washer method problem. But now let's recall what the formula for the washer method is. Okay, so it's pi big radius squared minus the small radius squared. Okay, so the significant difference here is now the big radius and small radius aren't just going to be given to us in the problem because of this offset, right? So because of this offset, now what we need to do is we actually need to add, you could also subtract, but in this problem, we actually add to the functions that we would normally bound this by. And the way you can see that is because this rate, putting the axis of revolution here is actually adding a separation distance by 2, is adding 2 to the radiuses. So like for this line, you see that the distance from the axis of revolution to the line y equals 1, that's a distance of 3, right? So you end up adding 2 to both of these things. So so the integral that we would want to set up here is an integral from 0 to 1, and for the big radius, that's going to be that's going to correspond to this exponential. Well, you would have the exponential as before, but because of this offset of the radius, you end up adding an extra distance of 2 to the radius function, and then you end up squaring that guy. So this is the big radius squared, and the small radius squared is going to be, well, the normally it would just be the function 1, then we add 2 to that, we square it. Okay. All right, and so we can go ahead and calculate this thing. Let's expand out the inside. So e to the x squared can be rewritten as e to the 2x. That's just an exponent property. And then you would have 4 e to the x plus 4 minus 3 squared is 9 dx. And so you go ahead and integrate this guy. So this is going to be a 1/2 e to the 2x. That's technically a u sub, but it's one of those simple ones that you should hopefully just be able to do by mentally. And then this is a -5, which is going to turn to a -5x when we integrate it. And we evaluate this from 0 to 1. Okay. Plugging in 0, or no, so yeah, both of them actually give you non-trivial things, so I need to keep a bit of track of this. So if I plug in 1 e squared over 2 plus 4e minus 5, and if I plug in 0, the thing is that the exponentials don't cancel completely, so you have to pay attention to them. 1/2 plus 4. And so we can still keep the 5 on the outside. And you see that the numbers will simplify a bit. So -5 minus 4 minus 1/2. So -9 minus 1/2. Minus 19 over 2. And so there you go. That's It's a bit messy looking, but that I can't see any other way of simplifying that value. Yeah. Okay. So are there any questions?
You might have already went over this, but your big radius, right?
Mhm.
That how would you find that necessarily? Because like on 2 you had 10x, but how does that describe the radius, I guess? You see what I'm saying?
Um, how to describe the big radius? Well, okay. My red is not so good, but you see that the this is the segment that will trace out the 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 washer. Do you see that?
Yeah. Yeah.
Okay. So the big radius is just going to be the distance that's furthest away from the axis. So in that case, that's going to correspond to this upper part of the segment, which is always going to coincide with the line.
Okay. So it's kind of like the outside, I guess, right?
The outside. Yeah, like I guess you could think of it that way. Yeah, if you treat this guy as outside and you treat the curvy one as the inside.
Oh, now I understand it. Okay. Yeah.
Yeah. So this is
I
making a
get it now.
really weird shape. Okay.
Yeah.
Mm.
I
Like
understand it now. Yeah, that
this is
makes
kind of
sense.
like a weird vase shape thing. You can actually put like liquid inside of it if you just rotate it.
Yeah.
Right. Yeah. Yeah. Okay. Yeah. Other questions? No. Okay. Well, I want to give you guys time if you want to ask any questions, but um, I don't have anything else to add to this. So, uh,
So if you were, right, so like let's say you had a problem where you had to use, I don't, let's say you didn't have to use the washer method, right? But you use the washer method anyway, wouldn't that just give you the same answer, right?
it should, yes, yes, yeah.
Okay.
These methods, it's all about the convenience of the setup. So, yeah, there are certain problems where you could actually use either method just because the shape is simple enough to be possible to work with. But yeah, but then there are some situations where you really don't want to use one method compared to another because otherwise you have to like cut up the shape and add different integrals together to make it all work out. But yeah,
Could you go up to when you wrote the formulas down?
the formulas. Yeah, okay. A bit more.
You had the shell method. I'm just looking at that. What's
Mhm.
the what's the difference between like the shell method and the, the washer? If you're just going around like the x-axis.
It's about what we what we're kind of tracing our what kind of like smaller shapes we're trying to sum up to create the overall three-dimensional shape. So like in these two pictures, the important thing is that in this picture we vary the x. Our slice is going like left to right, so we vary across the x-axis, and our small shapes are these discs. But over here, the line is horizontal, and so then we vary it up and down. We vary it across the y-axis instead. And that's going to trace out these cylinders instead. So the left side is actually summing up a bunch of circles, disks, and the right side is summing up a bunch of cylinders that are like inside of each other. Like,
Okay. And how would like the shell method, how would you read that? What
read it.
what would it, I mean like what would a question look like, I guess?
I mean, they look like the other 2 pages of the problem set.
Okay, so we'll go over that next.
Yeah, yeah. They look really similar. It's all about like what the function actually is and just how convenient it is to like create that line, that red line here. So there's nothing like you can't tell without drawing, I think. So I always need to draw it just to see.
Okay.
Yep.
Okay, thanks.
Right. Anyone else want to ask questions? If not, we will end early, I guess, as we have been doing for a while now. I'm gonna stop recording.